coming. So today I'll be talking about efficiently computing similarities to private datasets. This is joint work with the Arturs, Zenon, Sepide. My face is here, and Jakub. So so what is this talk about? So let's say you're a hospital and you have a bunch of private data of patients who had COVID, and then later these are private data sets. It's a private data set, and later you notice your dog is sneezing, right? And you want to test, okay, you want to ask, does my dog have COVID? So what do you want to do, right? You want to take your dog to the hospital, get its lung scanned, and you really want to measure the similarity between the dog, your own lung scan, your dog's lung scan, versus this private data set of COVID patients, right? So this seems like a well-motivated problem. So the talk is about how can we formalize this and can we get good algorithms for this. So what are the requirements, right? We want to preserve some notion of privacy between this private data set of previous hospital patients. And we also want to output an accurate answer, right? If your dog does have COVID, you want to say something close to yes. All right, so that's the high-level motivation. So now let's mathematically formalize the problem. So instead of having lung scans, that's kind of hard to work with. Every lung scan will be a vector in some d-dimensional space. So the hospital has some private data set of n points in d dimensions. And you yourself have a query, a point. And you want to measure similarity between your query point and this private data set of, let's say, prior COVID patients. So you pick some similarity function f. Let's say it's a Euclidean distance or a kernel function, just some natural function f that measures similarity. And you want to compute this following sum. You want to compute the sum of f of x comma y, where x ranges over this private data set, and y is your own data, okay? So now, like I said, we have two requirements. We want to preserve some notion of privacy between the data set, and we want it to be accurate as well. So let's formalize this a little bit further. So you can think of the hospital as an algorithm. It has as input this private data set, right, that it's collected. It wants to output a data structure. And what does the data structure help us do? Well, the data structure hopefully is able to compute an approximation to this sum. Really, the key thing is we want the data structure itself to be private. So the hospital can tweet this, like, hey, here's a Twitter, or here's a GitHub link for this data structure. So because the data structure itself is private, we can hope to make as many queries as we want, but we have to give up something, right? So we can only hope to be accurate sometimes. So let's just say we want to be accurate in expectation, like a small expected error, but it's really important that the data structure itself is private. So what is, like I said, we want this summary. You can think of the data structure as a summary of the data set to be private. So here is one solution, right? It seems kind of a hard thing to impose that we want to make infinitely many queries, but here's one example. If the data structure always outputs the number 42, right? Well, it doesn't depend on the data set. It just says something 42. Well, of course, it's always going to be private. It's saying one fixed number, but it's not very accurate, right? It might not, be truly reflective of what the value of the sum is. So now we can do something, right? Now the question is, can we do something non-trivial? So does that make sense? And the notion of privacy we're going to be using is differential privacy. It doesn't really matter what it is in this talk, because this talk is not really about differential privacy. But we've seen this previously in the morning, but it's some notion of preserving these the data of these private patients. Right, so to write this again, what we want is for any fixed query y, we want to have low expected error to the true sum. And the expectation is going to be over the randomness that we use to create the data structure, okay? All right. And like I said, right, we're gonna formalize this with the notion of differential privacy, but it doesn't really matter what that is. It just intuitively it means even if one patient's record in the data set which was changed or swapped, then the data structure we output is going to be similar. All right. But this talk is not really about differential privacy, so I'm not going to be too formal about it. Okay. All right. So what are the main results of this paper? This paper studies a wide range of possible functions f that we can use to compute similarities, like Euclidean distance, L1 distance, kernel values, and so on. and the trade-offs between privacy and the accuracy that we have, okay? So I'll mostly focus on this very central distance function, the L1 distance. You might think the L2 distance is more natural, but it turns out the L1 distance is more powerful, so it makes sense to study that. So one thing that we get is, like, remember we're interested in a sum. So it's a sum over n things, right? So you might expect that the error that we get should be, somehow related to n. But the really cool thing is we can get error that is sort of independent of n. So we have some small additive error at the cost of a small multiplicative error, okay? So if you compare this to prior work has, some small dependence on n. So I'm hiding, like, things that depend on epsilon, this privacy parameter, and some log factors, okay? But really the cool thing is, you can approximate this sum with error that doesn't depend on n at all. Yeah, and this data structure will be private. You can make infinitely many queries to it. It's very nice. Okay. All right.
Is the construction time for these datasets pretty efficient?
Yeah. So our runtime is like linear time. It's not so clear what the runtime of this prior work is, and you have to assume the data is bounded. So I'm assuming it lies in some bounded range. Okay. So it lies in, let's say, between 0. All the coordinates are between -10 and 10 or something.
So if you didn't care about runtime, is it possible to get better error using some?
Yeah, so there's a lower bound of additive error that's like, it has to be D, but I'm not sure about the multiplicative factor. So there's some things to improve upon here. Sorry?
Alpha constant?
Alpha is you can pick any alpha you want. So it's a trade-off parameter. So if you're willing to accept a little bit of multiplicative error, then you can get good additive error.
So just to understand the scaling of this, because I guess if I was to just double all the points, then I'm doubling the.
Right. So here's some assumption that the data has to be bounded. Yeah.
And bound is going to basically multiply your additive error.
Yeah. Exactly. Yeah. Yeah. Exactly. Yeah. Yeah. So yeah, you can't win by just scaling. Yeah.
Okay. Does the true value depend on n?
True value could depend on it, right? So the scale of this, right, is n times d, right? Because assuming they're lying some constant, bounded range, right? Because it's sum over n things, and each of things is sum over it's d-dimensional points. So the value is like n times d worse in the worst case. But even then, the additive error is very small. But the bounds don't matter. I think the more interesting thing is coming up. So hold on to your hats. And of course, in the paper, we study other natural functions, but for the most part, I'll only be focused on the L1 case, okay? So why did I choose to present this thing? Well, I thought, okay, I saw this workshop title, like Extroverted Sublinear algorithms. I was like, oh man, I think this paper is really extroverted in that sense. So I actually asked to give this talk, so thank you for allowing me. So why does this fit into this Extroverted Sublinear algorithms workshop? Well, I really think it presents, or it gives a new application of a template, of a meta template that I've noticed recently, between converting good sublinear algorithms to good private algorithms. And this is one other example of that. All right, so what do I mean by this template? So let's say we can first create, let's say let's ignore privacy stuff, and let's say we can first create a good sublinear time algorithm, meaning an algorithm that has very good query time for computing this sum, okay, for some distance function like L1. Intuitively, when we think of data structure, right, we think of an array of random numbers, right, and we can interact with this array, right? That's a mental model of data structure that we have, right? And then let's say we want to convert it into a private algorithm. Well, you can imagine, right, a common practice in privacy is to add noise. So we have this data structure. Maybe we change some bits from we flip some bits with some probability, right? And that preserves some notion of privacy. So this is just a template. This is not a formal relationship. This is a mental, like a template to have in your mind. And now, right, let's use this noisy data structure to compute our answer. Of course, how do we create this sublinear data structure? Well, that's where the thought goes in, but let's pretend we have that. So why does this sublinear data structure, sublinear time query data structure, imply a good private algorithm? Well, because it has sublinear query time, right? Like when a query comes, because it's sublinear, we're only going to interact with a few memory cells of the data structure, right? That's what it means to be sublinear. But because we only interact with a few memory cells, we're only like touching very few amounts of noise, right? Because we're only touching very few memory cells. So we're only accumulating like a very small amount of noise, proportional to the query time. So there's hope for a small error, right? Because we're only touching a small amount of noise. So in some sense, right, this gives some sort of reduction between, having a good sublinear data structure to one that has low error if you convert it to be a private data structure. Okay, it's very high level, right? Not formal, but this is the driving thought behind our results. Yeah.
This is sort of counterintuitive to me. So I'm wondering if you can maybe elaborate some more, because I think of these differentially private algorithms as having large noise on a per entry basis for the data that you get that's differentially private. And you need to sort of average a lot of it to get a reliable number. You're saying because you only touch a few elements, it's better. So I'm confused by that.
So I agree, like, averaging more noise, like, gets them to cancel. I guess this is maybe a little bit orthogonal. This is saying, maybe there's like some fundamental amount of noise you have to add because of some lower bounds. Well, in that case, right, a query algorithm that only touches like very few of those noisy cells would be good because you're not going to accumulate lots of noise. I guess it might be an orthogonal thing. Yeah.
A bit related to that, so you could see that template if your queries were non-adaptive, but
right.
It also works for adaptive things, right?
So that's yeah. So that's why this is not a formal reductions. It's not always going to be clear that you can do this. So that's why like the choice of sublinear data structure matters a lot. You don't want things to be super adaptive. You want things to be as non-adaptive as possible. But yeah, that's all I have to say. All right. Right, so the main point of this paper is actually to find good sublinear data structures to compute this sum, and somehow like converting them to the private versions is not the hard part. Okay.
Sorry, Sandeep,
Oh, yeah.
So when you say sublinear structures, you don't mean the size of the data structure.
Yeah, I don't mean the size. I mean the query time. Yeah, I mean the query time. Yeah. All right, so now let's go back to our L1 distance function, right? So I'll present the entire algorithm to you. It's very simple, so I like it a lot. Right, so what is the thing that we want to compute, right? We want to compute this sum. Given a query y, we want to iterate over our data set, this L1 distance. Well, what is the L1 distance? It decomposes into coordinates, right? It's the sum of absolute values. Well, anytime you see a double sum, I don't know, what do you think of doing? That's swapping, right? So if you interchange it, right, then you're summing over the dimension over endpoints. Then you can say, okay, you know what? Let me just make a different data structure for each of the d dimensions. So now I've reduced it to a one-dimensional problem. Okay. One-dimensional problems are nice because they're very easy to think about. And in particular, right, in computational geometry, there's this sort of holy mantra or chant, right? Like there's a tree hiding somewhere, and there's going to be a very nice tree for us that will help us solve this problem. So for now, let's just assume all your points are one-dimensional. You get a query point y that's also one-dimensional, and you want to compute the sum of distances. And for now, for simplicity, I'm going to assume the data set points are all in this like discrete set. This is without loss of generality by rounding, but for now, let's just assume they're discrete points. Let's make one more simplification, right? What is this sum? Essentially, if I know for this query point y, which I know, if I know like how many data points are within distance 2, within distance 4, and 8, these powers of 2, then all I really need to care about is sort of how many points are at that distance scale, and I can multiply by the size of that scale, right? So all I'm saying is so just pictorially, right? Let's say these x's are my data points that I have, and a query point y comes. I want to compute the sum from this to all the red points. I really don't care what the red points are exactly, right? Because I'm okay with the approximation. I just care about, in these, geometrically increasing buckets, how many points are in every bucket. So none of the things I'm saying is like particularly deep or novel. It's just that it's very simple and it seems to work very well. Okay. So it actually reduces to a further simpler problem, right? Given an interval, how many points are in that interval? Right. That's all I need to solve. Okay. So now where's the binary tree? So I think we've seen binary trees in at least 4 talks today, if I'm correct. But okay, here's another one. Right. So this is going to be the most natural way to do this. I'm going to have a bunch of leaf nodes, right? I rounded all my data. I'm assuming my data set is in some discrete set. The leaf nodes will count. So there's no privacy yet, so I'm going to add that later. The leaf nodes will just count how many points are at that leaf. The paired nodes will just store the sum of the children. Okay, so it's very natural. And now how do I perform an interval query, right? Well, for any interval, it's always possible to break it up into logarithmically many copies, logarithmically many smaller chunks, and just look up the counts in that many nodes, right? You just write in a binary representation, and mumbo jumbo like binary stuff works out. Sorry.
Can you use binary tree to do it without any approximation?
Yeah. But here, this is going to be good for privacy. So that's the part that's coming later, right? So of course, this is like, if you just care about this one-dimensional problem, I'm sure there's like optimal algorithms. But this one in particular is simple, and it's going to work really well for privacy in a bit. So now how do we make it private, right? So what does privacy say? It says if I change or swap one data point, how does it affect my output, right? My output is this tree data structure. If I if I add a point at 3, let's say, it's only going to affect the counts from the root to, from the leaf to root path, right? And each of those counts will be affected by 1, and there's only log n things along the way. So essentially, it only affects log n counts by 1. And that means, right, so there's like a common practice in differential privacy, which, if you can bound this sort of sensitivity, then you can add that much noise to all the, all the nodes in the tree, and then the tree itself will be private. Yeah. Right, so what is a tree, right? I'm outputting this data structure, this tree. You can imagine this tree as an array, right? Just like write the DFS. I'm saying, okay, if I change 1 point, right, I can possibly output 2 different arrays, but the sum of L1 distance between the 2 arrays will be only log n, right? So intuitively, what it means is it suffices to add log n, kind of noise that's order of log n to all the nodes and release the tree, and that's going to be enough to preserve privacy.
You're not concerned with like hiding any characteristic access targets or something?
No, right? Because all I'm doing is saying, just releasing. You can think of I'm releasing a vector, right? Right. Encode the tree as a vector. So now, what is the total error, right? Like I said, the query time is log n, right? And each node only has log n amount of noise. So I'm just multiplying 2 log n's. That's the total error. And of course, there's a d factor from having d different copies over every dimension, but that's pretty much it. Okay, so this is the entire analysis of the L1 algorithm, right? So I've showed you, right, the error only depends on log n factors, right? There's no n term in the error. So this simple approach works really well and gives much better bounds than some, I guess, arguably more intense methods of prior work. Yeah, and now, yeah, so you get actually d to the 1.5 because you have to do some composition theorems between, essentially, like the fact that you're building a different data structure on every coordinate accumulates some d factors. I think it ends up being d to the 1.5, or I think. Yeah, some d factors times some log n factors. More importantly, there's no like n factor, which I really care about. even though the sum itself, right, has scale that's like size n. So now why is this a good building block? Well, okay, the L1 metric is very powerful in the sense that lots of other metric spaces embed into it. In particular, right, the most natural version of this question is with L2 distance. Well, there's a really cool theorem. It's a variant of the JL lemma, which says there is an oblivious random matrix, which doesn't depend on your data points. It's a random matrix, so you can release it, such that the L2 distances before are equal to the L1 distance after applying the map. Okay, so basically, right, we reduce a very complicated problem, which is compute the sum of L2 distances. I don't know how to do that, to an L1 problem, which actually is a one-dimensional problem in disguise. All right, cool. And just for the other functions F we're studying, it was really crucial, right, to design such sublinear query time data structures. And to do that, we really had to exploit properties of the specific Fs that we're studying. So this, one-dimensional decomposition is very particular to the L1 distance. All right. Okay, so now, yeah. So for different Fs, you have to exploit different, so in the paper we wrote it as different functions have different lower dimensional versions of themselves. I'm not sure how to properly classify them, but essentially you have to find some low dimensional version, structure in the problem. Yeah. Okay. So the cool thing about these algorithms are they're very simple. And now let's go back to the motivation I started with, right, which is classification. So here's one experiment. I'm going to take an image data set with 10 labels, right? This is a CFAR10, and they're not going to be images; they're going to be vectors. But let's just say the input is vectors. For every label, I'm going to create a private data structure using some F, and any choice of natural F seems to work. And now when a new query comes, right, I want to classify it. I'm just going to compute the similarity between this new query point and each of the 10 labels. And that's going to be my label for this query. And this is sort of set up for differentially private classification, for instance, because because every point has a different label. So if I release a private data structure for every label, which is a disjoint set, right? This is private with respect to these input images, right? So I'm able to classify further points in a private manner, all right? So I'm going to show a plot, don't be scared. Okay, so this is a plot. So a lot of things going on here, but let me break it down for you. So what epsilon are we picking? In practice, people pick high epsilon, but here epsilon's 1. And there's also some notion of approximate DP, so we're also doing that, but forget about it. So this blue triangle is our algorithm, all right? Now, what are these two curves? There's another way to do differentially private image classification, which is you just train a neural network to be differentially private. So what you do is at every step, you just do, instead of doing gradient descent, you do private gradient descent. But the thing about private gradient descent is it takes a long time. You have to take a lot of iterations for it to output a good answer. So it's very, very costly in terms of time. So in particular, these are two state-of-the-art, DP image classification, neural network methods. So essentially, what you do is you say, okay, I know I'm going to run for 1,000,000 steps. I'm going to run gradient descent for 1,000,000 steps. That means every step of my gradient descent should be, epsilon over 1,000,000 private, so I can use composition theorems. So essentially, first you have to know how many iterations you're going to take, and you take that many iterations of DP, gradient descent, private gradient descent, and then you get some sort of trade-off between the runtime and the accuracy, because the more steps of training you do, the better your neural network gets, right? So in particular, these methods, it's not that you can extend this neural network to that neural network by doing more steps. You have to train from scratch because you have to go back and configure your epsilon to be smaller from the beginning. So anyways, the point is you get some curves like this from prior work. So in terms of accuracy, right, we're not, it's not the best, right? Our method is not the best. But our method actually doesn't require any private training. It's actually just take a bunch of vectors, create a private data structure, and just compute, L2 distances essentially. Whereas these methods are very expensive, right? This is on my, cheap, or not cheap, but my personal laptop. This is on an expensive GPU. I think 10 to the 5 or 6 is around a couple of hours. This is like almost free, like this. So even though it's not, competitive, if you just look at the y-axis, it is like, much, much faster. Sorry?
Can you combine them, use yours for
Inherently, no, because they're very different methods, right? This is just like, this is a data structure to compute distances. This is a neural network that's going to give you a label between 1 and 10.
Is that
Basically, yeah.
time or
Sorry? So this is actually just, all right, so this is, this is dominated by construction time. So I think this plot is only the data structure construction time, but even query time would be maybe even worse. Like the gap would be even bigger. Query time here, right? Like this is I didn't mention it, but these are actually sublinear time algorithms also. So the query time is on the order of nanoseconds even, whereas you still have to like inference on a GPU. So it's going to be on the order of milliseconds. All right. Hopefully that plot makes sense. Okay. And like I said, right, going back to my comment in the beginning, this is not like the first time this has happened. There's been lots of other cool connections between, some notions of sublinear or local algorithms and private algorithms. There's a nice survey that Safia wrote. I think she's also in the audience. So I would definitely recommend reading that. And I think there's lots of other cool connections to be found between sublinear algorithms and private algorithms. That template I presented is just a meta heuristic, but hopefully, more problems can be solved using that. All right. Yeah. So I didn't want to take up too much of your time because I knew it's a nice, beautiful day. So I'll say, thank you, and yeah, don't forget to stretch. You've been sitting here for a while. All right.
So that was one of the F's you
So what exactly is the F here? What do you mean by correlation?
X, Y is, I don't know.
Right. So those are actually like pretty easy to do because essentially an inner product, sum of an inner product is just one inner product. So you just, you don't even see the end part at all.
Yeah, normalized.
Yeah.
So the way you set up your problem, there's only like one query point.
Yeah.
Right? Because you're doing the expectation.
Right.
But do you have a sense of like, if you had k query points, then like, or how many queries can you make before things become erroneous?
Right. So it's pretty. So there's another way to write the bounds. Like instead of expected error, you can write like small additive error with high probability. So there's an equivalent way to do that. Essentially, what you can do is you can just make like multiple copies of the data structure, but you have to scale down the privacy parameter a little bit. So the additive error increases by some log n factors, but now the failure probability is like, so if you make t copies, right, the additive error maybe increases by t, but the failure probability is now 2 to the negative t. So you can do that too.
For some of the app, I think it has very small sensitivity. You add some local noise to your input data and then construct the data structure after.
Maybe for specific apps, but in general, that's going to be a very bad idea because each like single f of x, y can vary like, up to constant numbers, right? So, and you're summing n things, right? So you can get error up to scale O of n. But here, like, we're not seeing any n factors. That's the cool thing.